All right. So I do want. Oh, I hit the wrong button. I do want to talk a little bit about an extra credit opportunity. Okay. All right. So at 10:50 will become available a problem, much like this one. Okay. Where you'll start with a fifth degree polynomial. You'll break it down and figure out how to write all the zeros and write it as a product of linear factors. Okay. So much like the last problems on the exam, a little bit more complicated because this is the stuff that we did on the Wednesday before your exam. So let's just go through one, make sure we all are on the same page of what I want. Okay. So first off, they tell you that negative 2i is a 0. Okay. So just like before, we'll run the synthetic division through. You can bring down your 2 and then multiply by your negative 2i, so you'll get negative 4i. When we add down here, can we combine those two together? Is it possible to combine those two together? No, so we just get the negative 5 minus 4i. And you might remember that these take a little bit more work with the multiplication, right? Sorry, I hit the... Hello, turn back on. I bumped the off button. There we go. Sorry about that. I bumped the off button. All right. So remember that it takes a little bit more work with doing all the multiplication. I don't want the multiplication to get horrible on you. So there are lots of different complex number calculators that you can get online. Okay. So I just did complex number calculator, Googled it. Symbol Lab is one of the first ones that comes up. It's pretty easy to use. Just right there where notice it says enter a problem right there. Right? Okay. So I can just take, I'll put parentheses around it just to illustrate what is going on. I can take the negative 2i, what was it, negative 5 minus 4i? Is that the other number we're multiplying by? And then just hit go, and it gives you the answer. Okay. So remember last time we talked, or not last time, but last Wednesday we talked about writing it off to the side and doing all the distributions and all that stuff and make sure we simplify it. If you just use this calculator, you don't have to do all that. You can just get the answers, okay? All right, so going back over, the answer is negative 8 plus 10i. We'll add down and get negative 4 plus 10i. I'm not going to flip back and forth 20 times here. So 20 plus 8i. Negative 3 plus 8i. Oops. 16 plus 6i. And then you'll get just a 6i. Multiply, you'll end up with negative. What did I do wrong? Somewhere along the line I made a messed up. Because I should get 0 when I'm done. But I get positive 12. What did I do wrong? It's an 8i there. Oh, goodness. Positive 10. Positive 8i. Positive 6i. Let me go back through here again. Negative 4i plus 10i and a minus. That's 8i squared. It's a minus 4. Eight minus 8 minus 4 plus 10. Where is it? Is it oh, it's just that's much better. Thank you. Somewhere along the line, I knew I made an error somewhere. Thank you. Try that again. This should be positive 16 minus 6i. That's good. Why did I know something was wrong? What do we have to end up with at the very end? 0. Good. All right. I'm trying to go through this to tell you what I want. All right. So the very first part of the problem that you're going to have for your extra credit is going to be something like this. It's going to ask you to type in those coefficients. Okay? That's the first part it's going to ask you. Right? So it's going to ask you, run it through the synthetic division the first time. The first answer you're going to type in is that one. Okay? Then it's going to ask, since we know that we have a complex number as a root, as a 0, what else has to be a 0? In this case, what else has to be a 0? If negative 2i is a 0, positive 2i, right? It has to be the conjugate, right? So that's your next part. We'll take the 2i through. Bring your 2 down. Multiply by 2i. Add down. Get negative 5. Multiply. Get negative 10i. Add down. Get negative 4. Multiply. Get negative 8i. Add down. We get 3. Finally, 6i. Again, this last number has to be a 0. Also, what has to be true about all of these coefficients? Can they have any i's in them? No. When you run through a complex number and then its conjugate, those all have to be I-free. Right? Okay. What was the degree of the polynomial we started with? 5. How many times have we run through? Twice. So what would be the degree here then? 3, right? Because we've taken out 2 of the degrees, right? Okay. So far, where are we at? We're at f of x equals x plus 2i, x minus 2i, and then 2x cubed minus 5x squared minus 4x plus 3. That's so far, right? All right. Then I'm going to ask you, looking at this polynomial, not the original, but this polynomial that I just underlined, what are the possible rational roots? Right? So what are we going to look at for the possible rational roots? Yeah, factors of 3 and factors of 2. What are your factors of 3? 1 and 3, and for 2 is 1 and 2. So if you do your possible rational root, bless you. What are your possible rational roots? 1.5, 3. Good. Okay. Now, so you don't have to worry about typing in plus or minus. I'm just going to ask you for the positive ones. So on Moodle, I'll just ask you for what I have in the braces there. Just that part. Notice it was easier to list them here than it would have been originally, right? Because originally you would have had factors of 12 to do, wouldn't you? Rather than factors of 3. So again, the problem's going to be run your complex root through, run the conjugate through, okay? And again, at each step, the first step, you're going to write down these coefficients for me. The next step, you're going to write down these coefficients for me. Okay? Then it's going to ask you for the rational roots. Then it's going to ask you to make a graph. So maybe go over to Desmos and take a screenshot. If you go to Desmos, I got to remember what the numbers were. 2, -5, -4, 3. I can do that. So I'll go over to Desmos. We had, graphing calculator, 2x cubed. Of course, I just forgot it was the 4. I forget what was the 5 first. 2 minus 5x squared. Squared minus 4x plus 3. And then it's asking for a rational root. Which one might you try? The 3? All right, the 3. Okay. All right, so go back over here. Run the 3 through. So just to go back over here. Oops, let me change my color. Bring down the 2, multiply, add, multiply. Interesting. What did I do wrong? Did I type in the wrong function? 2 minus 5 minus 4, 3. Having a fun day today. Oh, it's negative 1. Oh, it's positive 1. Thank you. Good. I keep messing keep messing my sign up when I'm adding today. Sorry about that. Okay. All right. It's really good illustrating what I want you to do if I can't do it right. All right. So this means that finally we've got an x minus 3, and now we're at a quadratic, right? 2x squared plus x minus 1. And again, this one's going to factor, but if it doesn't factor, what can you always use at this point? Quadratic formula, right? This one actually factors as 2x minus 1 and x plus 1. So our zeros here will be negative 2i, positive 2i, 3, 1/2, and negative 1. All right, so again, first part will ask you for that first set of coefficients after you run the complex number through. The second one will ask you for the second set of coefficients when you run the complex numbers through. That second set should have no i's in it, right? Then you will be asked for possible rational zeros from the cubic that is left. Upload a graph that you're going to use. Okay. Run through the rational root that you think works. Get the quadratic. And then use probably quadratic formula to get the other 2 roots. Okay. Again, I'm going to give you 90 minutes to do it, just like the previous quiz that we had. It's going to be in the same spot in Moodle where the quizzes were. Okay. So like I had the previous quiz, all of it will be on one page, so you'll have the function there the whole time. Right. All told, you can get 10 points back for your test. Okay. So you can get 10 extra credit points on your test. Okay. Sound like a plan? All right. Let's then talk about some new stuff today. Yes? Oh, it closes tomorrow night at 11:59. Thank you. Yep, tomorrow night at 11:59. Sorry, I forgot to mention that part. Thank you for asking. I also have it set up to set a reminder tomorrow too. So, all right. All right. This section's all about what we refer to as rational functions. The root word of rational is ratio. That's the root word of rational is ratio. So we've talked about rational root numbers in the previous sections because we were making those possible rational zeros, right? We said rational zeros, but what did we really make when we made out the list? What kind of objects did we make? We just did it a second ago. What kind of objects did we make when we wrote out all those possible rational zeros? What kind of object? What kind of number? Fractions. Good. It's that dirty 8-letter F word, right? Okay. Fraction. Right? We made fractions. So that's exactly what we're going to do here for rational functions. It's going to be a fraction, okay? But what we mean by the fraction here is going to have not just numbers, but we're going to use polynomials for our top and bottom. So a rational function is one that can be written in the form p of x over q of x, where p of x and q of x are polynomials. Okay. So think about how you've created numbers, if you will. You have your nice whole numbers, right? Those positive things, and then maybe you did some negatives, but then you start making fractions, and then your numbers started to get worse, right? Okay. Polynomials are kind of the function equivalent of integers. They're kind of your really nice functions. Really, all you ever have to do in any polynomial is add. Multiplication is just adding fast. Subtraction is adding backward. Exponentiation is just multiplying really fast. So it's adding really, really fast. All right. So polynomials are really, really nice. Rational functions are built out of those nice types of functions. Okay. All right. So if I'm looking at for domain, because anytime we create a function, one of the things that we might want to know is what possible numbers can we plug in? Since we've created a fraction, what do we need to worry about? If we're creating a fraction, what kind of thing do we not want to do? What do you not want to plug into the bottom of a fraction? What can you not divide by? 0. There we go. Okay, we've done problems like this before, right? So if we're worried about domains for a rational function, I'm worried about where this thing is equal to 0, right? So we need to worry about the values of x that make the denominator 0. We've already talked about this before, haven't we? All right, those are bad numbers. When we plug something in for x and make the denominator 0, we're trying to divide by 0, bad things happen. All right? We rip open the space-time continuum. All sorts of bad things happen, right? All right. So what we're going to be interested in this section is properties of rational functions and start to get a decent looking graph of them, kind of like what we did for polynomials with zeros and in behavior. So one of the things they're going to want to know about rational functions is where we might have problems. What's going to happen when we try to plug in something that makes the denominator equal to 0? So let's look at this example with y equals 1 over x. What's a bad number to plug in for x? 0, right? So we notice that the domain here is everything but 0. And what happens when we try to plug in numbers that are close to 0? For example, if I just make a little table here, if I put x equal to a half, what do you end up getting out? Not a trick question. What do you get when you plug in a half? It'd be 2, right? It's 1 divided by a half. What do you do when you divide by a fraction? Multiply by the reciprocal, right? Basically, this function is telling you to take the reciprocal. That's what 1 over x does. It says reciprocate, right? So if you say plug in a fourth, what would you get? 4. If I tell you to plug in a tenth, what do you get? 10. If I tell you to plug in 100th, what do you get? 100. When I start making this number really, really small, really, really close to 0, what happens to the output? It gets really, really big, right? Okay. So what we notice here on the graph, hopefully, is that I get really, really, really big numbers the closer I get to 0. Right? Now, also, what happens to this, if x gets really, really, really big, we're also going to make our fraction really, really small, right? So we get a piece that looks like that. What happens if I would have put negatives in there? If I would have had negative a half, what would you get out? If I put a negative a half, what would we have got out there? -2. If we put a negative a quarter, we would have got -4, right? So basically, you just get a mirror image of that down here. We've already seen graphs of this type of function earlier in the semester. That's one of those catalog functions that we talked about earlier. But this is the kind of analysis that we're going to want to do with this type of function. All right, so what happened when I try to put something close to 0 in? We got something, either a really, really big positive or a really, really big negative. It gets closer and closer to that vertical line. So we refer to this vertical line here as a vertical asymptote. Okay. So in this case, our vertical asymptote was x equal to 0. Notice that the 0 that we're getting for our asymptote is exactly what we could not plug into the domain, right? That's what's missing out of the domain. So what we're going to discover going forward is that our vertical asymptotes in our domain are going to go hand in hand. Okay. Now, you have to be a little bit careful because not every domain issue is going to give you a vertical asymptote. We'll see that here in a second. But that's what you need to pay attention to for vertical asymptotes. All right. So let's look at this one, where it asks you to find all vertical asymptotes of the function x plus 3 over x minus 2. Where do you see a domain issue? What number can you not plug in for x? 2, right? Okay. So for our domain here, we have negative infinity up to 2 and 2 to infinity. Let's see what happens around 2 just by doing a quick graph with a calculator real quick, a graphing calculator. And then we'll come back and do some, see if we can figure out some analysis of what's going on. All right, so I'm going to kick over to Desmos real quick. We had x plus 3 over x minus 2. Minus 2. So there's what a graph of that looks like. If I zoom out just a little bit more, we can see that we're getting really, really close to that line, x equal to 2 here, right? Now, going back over to the problem here, notice that when you put 2 into the denominator, we would get a 0. Did we get a 0 in the top at the same time? Or do you get a number other than 0? Not a trick question. What do I get when I plug 2 into the top? Not everybody all at once. We put 5, right? We get 5 in there, don't we? Got it. All right. So notice on top we get a 5. On bottom we get 0 if we try to put in 2. Okay. So if I take some, like in the previous example, what did we do? We put in 1 divided by a half, we got 2, right? But 1 divided by a quarter, we got 4. If there was a 5 on top, would that make much difference? If you took 5 and divided by something really small. If I took 5 and divided it by a tenth, what would I get? If I take 5 divided by 1/10. We get 50, don't we? Right? Or we take 5 divided by 100th, what do we get? 500, right? If this number is close to 5, I'm still getting really, really big numbers out, right? So in this case, we do see that we get a vertical asymptote. At x equal to 2, okay, where the denominator is equal to 0. And we'll talk a little bit about how we can get what the graph looks like in a minute. But right now we're just worried about what the vertical asymptote is. Okay. So on the graph, oops. We would have this vertical line. Now, be careful. That vertical line is not really part of the graph. It's just a guide to help us draw. Okay? Now, some other pieces that will also be able to help us will be, pardon me, we'll get some we'll get horizontal asymptotes if there are any. We'll talk about that in a little bit. But we'll also use intercepts. So let's think about how we find the x and the y intercepts and see if we can get a graph that kind of matches what we did in the previous, what we saw in Desmos. That's our goal, by the way. How do you find y-intercept again? What do you do? Yeah, plug in 0 for the x, right? We get negative 3/2 for that. So we'd have the point down here, right? How do you find the x-intercept? Yeah, you said the function equal to 0, right? Now, again, we're dealing with rational functions. Rational functions are fractions. What needs to be true to make a fraction equal to 0? Bless you. What needs to be true to make a fraction equal to 0? The top is 0, right? We need the top equal to 0. So our x-intercept would be negative 3. And now we can see a little bit about how this would get drawn. It would go that way. It's not great. Okay, that part would go that way. And then from the other knowledge that we'll have later on, we'll also see that this one will go this way. And we get a graph that kind of looks like what we saw in Desmos. It's not great right now because we need one more piece of information that we have not talked about yet. Okay. But again, right now what we're talking about is when we get close to that asymptote, it has to go get really, really close to that line. That's the idea. Right. Let's look at this next one. Where do you see a domain problem? What can't you plug into the denominator? Negative 3. Now, in the previous examples that we've seen, we noticed that there's a vertical asymptote when we've put something when we've had a problem in the denominator, right? Let's see what happens on this one when we plug it into Desmos. The top is x squared plus x minus 6. The denominator was x plus 3. Do I see any vertical asymptote there? No. I just see this thing that looks like a line, don't I? Let's investigate what happened. Something happened. Something is different, right? Right? Something's different. Something is not the same. Okay, let's go. Let's look at what happened. All right. So notice that we said that for the domain, we certainly cannot plug in negative 3. Right? Can we factor the numerator? Does the numerator factor? Yeah, x plus 3 and x minus 2, right? Do you notice anything that can happen when we factor? Yeah, it looks like the x plus 3's go away, right? So this is equal to x minus 2 so long as I don't put in negative 3, right? Notice that the original function was not in lowest terms, okay? So I'm going to write that down. Original function was not in lowest terms. Okay. So in order to find vertical asymptotes, you need to put your rational function into lowest terms first. Okay. Don't just say that there's a vertical asymptote here at -3. That doesn't work. Okay. You have to make sure you're in lowest terms. In this case, we need to factor the numerator and cancel. If I didn't worry about this x minus 3, or the x not equal to -3, and just looked at this function, x minus 2, what kind of a graph do you get? What kind of a graph is that? What kind of a function is that? If I think about it as y equals x minus 2, what kind of a function is it? Bless you. We talked about them earlier this semester. You know this one. I promise you know this one. Y equals x minus 2. What kind of function? What kind of graph do you get? What kind of an object is that called? A line. Yeah, it's a line, right? What's the slope? What's the slope? It's 1. What's the y-intercept? -2, right? Wasn't trying to ask tricky things, right? So we get a line. Now we have to be a little bit careful. What did we say we can't plug into the original function? -3, right? So when I get over to -3, I end up having a hole. I have a little hole that's in there. Okay. So the reason why there's a little hole there is that because, again, we can't plug in -3 into the original. Okay. Bless you. Notice I didn't show up in Desmos, did it? Okay. Because there's just a little bitty hole, right? So when you put something in a graphing calculator, all your graphing calculator does is plug in numbers and place connect the dots. So what that means is that on the graphing calculator, it didn't plug in exactly -3. And so then it just traced over the hole. So you have to be a little careful with the graph in that case. But this one has a little bitty hole in it rather than a vertical asymptote. All right. But the moral of the story is that in order to find vertical asymptotes, you have to put your function into lowest terms. Okay? To do that, let's look at this example. To put it in lowest terms, you're going to want to factor the numerator, factor the denominator, and see if anything cancels. Okay? So how does your numerator factor in this case? Okay. And how does your denominator factor? All right, so does anything cancel in this case? Any common factors? Anything in common? No, nothing's in common, right? So there's no canceling. So this is in lowest terms. All right, so if it's in lowest terms, then all I need to do is worry about what makes the denominator equal to 0. So what makes the denominator equal to 0? +4 and Positive 1. Now again, asymptotes are lines. Lines are described algebraically as equations. So don't just write 4 and 1. That's not a line. 4 and 1 are numbers. Okay? Write x equals 4, x equals 1 for vertical asymptotes. Okay? So again, what's the process? Just to make sure we remind ourselves what the process is. I need to know when the denominator is equal to 0, but I also want to make sure the numerator is not 0 at the same time. Okay? So step 1 is make sure you're in lowest terms. Okay? That typically involves factoring the top and bottom and seeing if you have any common factors. Okay? That's step 1. Okay. All right. Any questions on that one at all? All right. Well, let's talk about horizontal asymptotes now. Horizontal asymptotes, this is basically end behavior of rational functions. That's what we're really interested in. Remember we talked about end behavior for polynomials? By the way, what did you look at again to figure out end behavior of a polynomial? Which term were you interested in? The highest degree term, exactly right. Right, we're looking at a highest degree term. That's going to come into play with rational functions as well. Okay? All right. So let's look at y equals 1 over x minus 1. First off, let me ask you, where does that have a vertical asymptote? Heard it whispered. It was at 1, right? X equal to 1? Yep. Okay. So this one definitely has a vertical asymptote of x equal to 1. Okay. Again, that's because the denominator is equal to 0, but the numerator is not, right? It's already in lowest terms. Okay. But what about horizontal asymptote? Well, we're interested in end behavior for horizontal asymptotes. So again, what happens as x gets really, really big in the positive direction, and what happens as x gets really, really big in the negative direction? That's what end behavior is, right? Does your numerator ever change in this problem? Does the numerator ever change? No. Okay. So all we're interested in is looking at the denominator. If I put really, 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 really big numbers in there and do 1 over that, what do the numbers become? Are they getting bigger or smaller? So for example, if I put 101 in for x, what do I get? 1 over 100, right? If I put 1,001 in for x, what do I get? 1 over 1,000. If I put 1,000,001 in for x, what do I get? 1 over 1,000,000. What are those numbers getting really, really close to? 0, right? Because 1 over 100 is 0.01. 1 over 1,000 is 0.001. 1 over 1,000,000 is 0.000001. I have one too many zeros in that one, but they're getting really, really close to 0, right? Okay. So if I look at a graph then, what that means is we said we had a vertical asymptote at 1, but as we get really, really big, it's getting really, really small. So we're going to end up with something that looks like this on this side, and it'll look like this on this side. And we'll talk a little bit about why I know it has to go this direction on Wednesday. But it gets really, really close to, I'm going to put it in red, that horizontal line. So we say that this has a horizontal asymptote of y equal to 0. So what we mean by a horizontal asymptote, just to write a little bit of a definition here, a horizontal asymptote is a horizontal line that the graph of a function gets really close to as x goes to infinity or as x goes to minus infinity. That's what we mean by a horizontal asymptote. So we're trying to see if a line gets, or a graph gets really, really, really close to a horizontal line. Okay. Again, it's this end behavior idea. All right, let's look at this next example. X over x minus 1. Now, remember in this previous example, I asked you, does the numerator ever change? And you told me no, right? In this next example, does your numerator change in this one? Yeah, it does, okay? All right. Now, let's think about what happens. Let's think about just plugging in some numbers here. If I plug in 10 for x, I get 10 over 9, right? If I plug in 100 for x, we get 100 over 99. If you put in 1,000 for x, you get 1,000 over 999. Is there much difference between 1,000 over 999 or 1? Not much difference, right? If I do 1,000,000 over 999,999, that's really close to 1 as well, doesn't it? In particular, as x gets really, 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 really big, does subtracting 1 off of it do much to it? No. Okay. So what we're going to be looking at for horizontal asymptotes is the leading terms here, these pieces here. Okay. Our degree of the numerator is 1, and the degree of the denominator is also 1. So what that tells us is both have similar end behavior. So how do we find the horizontal asymptote if they have similar end behavior? So what this is telling us is that essentially, as x goes to infinity, or as x goes to negative infinity, the function is essentially x over x. We don't worry about the minus 1 has little effect, right? What does that simplify to? If I just had x over x. What does that simplify to? 1, right? So what that tells us is that the horizontal asymptote is y equals 1. Let's see if we can apply the same principle to the next part. Looking at the x squared over x minus 1. Again, think about it from an end behavior standpoint. Again, for polynomials, what do you look at for end behavior? What matters as far as end behavior goes for polynomials? What matters for polynomials? End behavior, what matters? The highest degree term, right? So as x gets really, really big, what matters on top? For this function, what matters on top? On top of the fraction, what matters? And this one. What's the highest degree term on top? Yeah, it's the x squared. That's what matters, right? What matters on bottom? Just the x, right? We're ignoring. Remember, we're just looking at end behavior. All we care about is the highest degree term, right? So for the end behavior, we have essentially x squared over x, right? What does that simplify to? Just an x. What's the graph of y equal x look like? Diagonal. Is that horizontal? Not a trick question. Is this horizontal? No. No, this is me moving my arm back and forth for whatever reason. Okay? That's not horizontal. So in this case, this tells us that there is no horizontal asymptote. Okay? So again, the idea here is that we're looking at the end behavior and seeing what happens. All right, so let's look at this next one here. Actually, let's look at the next two. And then we'll talk more about this on Wednesday. Horizontal, yes. Yeah. Okay. All right. So let's look at this one. What matters on top? X. What matters on bottom? X squared. All right. So if you look at your end behavior again, we'd have x over x squared. What does that simplify to? 1 over x, right? Now we did 1 over x as an example earlier. As x gets really, 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 really big, what does 1 over x do? It's really, really small, right? So what do you think the horizontal asymptote here is? If we're going to get really, really, really small. What are the numbers getting really, really close to? 0. So the asymptote is going to be y equals 0. Yeah. How about this last one? What do you think is going to happen there? What do you think we're going to look at for end behavior? X cubed over x. What does that simplify to? X squared. Is that a horizontal line? No. And it gets really, really big, doesn't it? So what are you going to say about horizontal asymptote here? Is there one? No. All right. Finally, the last one here. What do you think we're going to look at there? 2x squared on top. On bottom, x squared. And that simplifies to 2. So what do you think the horizontal asymptote is going to be here? 2. Yeah, y equals 2. Good. So that's exactly what we're going to look at for horizontal asymptotes, okay? So we'll summarize this next time, do more examples, talk about one more type of asymptote, and that'll get done with rational functions, and then we'll start some inequality stuff. Don't forget, you've got your extra credit opportunity due at midnight tomorrow night.